on computer. Ah, okay,
Cool.
all right. So let me read this one. Oh, actually, let me share my screen so I can show you my work. And I'll use this as an opportunity to point out one of the words I see right away here in number 6 is that it says it's elastic. And so be on the lookout for a couple of words. One is elastic. What that means is that and you can say this in either way, it means there's no loss of kinetic energy. Okay, that means that whatever kinetic energy you had before the collision, you also have after the collision.
Okay.
Another way of saying the same thing is to say there's no heat energy created during the collision. You would write it as a WNC, a non-conservative work. And so that would equal 0. So if I start off by saying, okay, 1D, and the problem right away, the title says elastic. Now, just because the title says elastic, I guess doesn't technically mean it's elastic, but just reading the title makes me think that this is an elastic collision. And what does that mean? So as I read it here, it says cart number 1 moving with a speed of V naught. So I'm going to put like a cart here and have it moving along. And it says it's moving with a speed of V naught. And maybe just to distinguish it, I'm going to put M1 here for the mass of that first cart. And it says it collides with cart number 2, which has double the mass of number 1. Okay, so I'm going to draw cart number 2, and I'll just put M2, which equals twice M1. Let's see. Cart 1, moving at speed naught, collides with cart 2, which has double the mass and is initially at rest. So this speed, but I'm not sure how to label it. Maybe I should label this as V naught 1 equals just V naught, and V naught 2 is equal to 0. So this one's stationary, this one's moving. Okay. The carts have springs that make the collision perfectly elastic. So there was that key word I was saying. If you ever see that word elastic, they're trying to say that the work done by the non-conservative force, that would be the rubbing, so that'd be the friction, the heat, would be 0. And so how it gets accomplished is, in a lot of ways, usually, and you can see it in the wording, usually there's a spring. So when they collide, the spring kind of gets compressed and then it kind of bounces off. So instead of having like a smash and a rub and have energy go into that, the energy goes into compressing the spring and then bouncing off. So ultimately, there is no loss in kinetic energy. Okay. But the real key is that word elastic. Now, there are, as long as we're doing this problem, a couple of other things. Inelastic means, of course, just the opposite of that. It means there is some heat. Okay. Usually those problems are a little harder because you just know there's some heat, but you don't know what its value is. At least this one, its value is 0. So if they just say elastic, it's not as much information as to saying it's inelastic, because inelastic, they actually tell you what that number is. Now, I will say there's other words that they use. Sometimes they use the word perfectly inelastic. Now, what's nice about that one is that really means they stick together. And the reason that's helpful is because you know that the two have the same final speed after the collision. Well, and maybe I shouldn't dwell too much on those, but those are the kind of words you should be looking for. Now, the other thing you should be looking for is once they say collision, I always like to just kind of set my paper up this way and say, all right, the momentum before, and so I like to kind of just put a little before, is the same as the momentum after. And that's really the big lesson of this chapter, is that if you have two things interacting, okay, and they interact just with each other, then one object loses the same amount of momentum as the other one gains. Maybe I'll leave it at that. I won't show you the proof behind that, but just know this, then, if you're ever looking at a problem and they start saying, hey, you have a collision, know that if you look at the two together, the momentum before equals the momentum after. In other words, what one person loses, the other person gains. I guess it'd be a little bit like two people playing a game of cards with real money. If one person loses, the other person gains. There's no other place for the money to go if there's only two people playing. And that's what we have here. We got just two things interacting. One loses the momentum, one gains. So just looking at this, it kind of seems to me what's going to happen here is number one's going to slow down and number two is going to start moving. So number one loses some momentum and number two gains. And they're probably the same amount. Okay. So I kind of like to start off then and say, okay, so here's what that would mean. That would mean that M1 times its initial speed, V naught. So that's the initial momentum of number one. Number two, I want to just put a 0 to make sure that you realize I'm including both objects, but the second object has an initial speed of 0. So when I take its mass times its initial speed, I get 0.
Mm-hmm.
So this right here is the total momentum, and I'll just write it as M1 V naught. So that's the total amount of momentum before the collision. So then if they collide, and they, I guess I don't really know much about it. I don't know if the first one bounces backwards. I don't know if it keeps going forward. I think he might say something if I keep reading here.
It does have a hint, yeah.
Okay. So the final speed of cart number one is V1, and the final speed of cart number two is V2. So maybe in my picture here, I'll draw a picture of after the collision. So I have this M1, and it'll be moving with a speed of V1. And even though I'm going to draw it kind of what I'll call the forward direction, keep in mind that this could be bouncing off, which often happens when you hit something that is more solid. And so I'm pretty sure this one's going to be a negative velocity. I'm pretty sure it's going to back off a little bit. In fact, look at his next sentence. He says, hint, cart number one has less mass than cart number two. So it bounces backwards. V1 is in the negative direction. Okay. So we could either think of V1 as being a negative number, or we could say it's absolute value, but it's going backwards. Why don't we just think of it as a negative number?
Okay.
That way, I don't even need to worry about the hint. The hint will fall into place when I go to solve for V1. If that's what they're asking for.
They are asking for V1 in this one, and they give us V naught.
Okay, yeah. So in number, let's see, how does this work here? Number 6, they give us V naught, yeah, and ask for V1.
Mm-hmm.
So that's going to be a negative number, unless in the answer key, he wants just the magnitude. Now let's see how it plays out. All right. But in my picture, I'm also going to then draw M2 and then say it's moving with some velocity V2. So here's where I would put my conservation of momentum and say, okay, so this is M1 V1 plus M2 V2. Now, as I look at his solution, he does this, and I guess I should ask you, would you like me to follow more his solution? Because he says from the hint, we know that V1 is in the negative direction. So he puts a negative and then really is solving for the absolute value. So maybe I'll follow his hint. So maybe it'll be more helpful to you and anybody else.
Yeah, I'll go ahead. I'm okay with that one as well. So
Okay.
that's the.
So
okay,
we're actually going to solve for the absolute value of V1 instead of what I said originally, which was the value of V1. So we're going to get a positive number because we're doing the absolute value of V1.
is that a negative mass 1?
Well, so then, yeah, I just, the negative was really for V1, so I put it out in front.
Okay.
Maybe I should have taken an intermediate step. Maybe I should have wrote this as M1 times the negative of the absolute value of number 1.
I see. Okay.
And then I can move the negative out in front. Yeah, so I was just doing too many math steps. I shouldn't have done that much math step.
No, it's okay.
Okay,
That makes
so
sense.
that is the, and I'm just going to put a little circle around that because I'd say this is the lesson of this chapter. Okay. However, earlier chapters, we learned about energy. So let's not forget that. So we had something like initial kinetic energy plus initial potential energies plus any energy added due to this non-conservative force is then equal to the kinetic energy after, I'll go final, and the potential energy. So that's what you did last week. And so, or maybe it was 2 weeks ago, but
Can't remember.
somewhere in the past and fairly recent past, you did conservation of energy. So let me do that step and then fill in what we know. And this is where that key up here comes into play, the non-conservative work. The fact that they use the word elastic. The other thing I can do is say, well, there really is no potential energies. The potential energies, there were 2 of them. One had to do with gravity, and the other one had to do with springs that were compressed. Well, we don't have any springs, and we don't have anything going uphill or downhill. Based on the picture, I guess technically the problem doesn't say it's a level cart.
It does say that it has springs, but it says it makes the collision perfectly elastic.
Oh, yeah. So I guess but the spring would just do this. The spring would momentarily compress and then stretch back out. So your starting potential energy would be 0, And even though it compressed during the collision, it ended back in its
Gotcha.
extended form.
So
So
that's its beginning and end points.
right.
Okay.
So it, and then that's kind of the neat thing about energy. We don't have to worry about the stuff in between. And so even though there is a spring, and thanks for pointing that out, because I think I said there was no spring, and that's not quite true. And that's a better way of saying it is there is a spring, but the spring starts off with not being compressed, and it finishes not being compressed. So its energy is zero in both those cases. And so that's why I was saying, if that's the case, then initial kinetic is also equal to final kinetic. And so that's why I was saying a problem like this that you called elastic, if it doesn't have this heat and it doesn't have a compressed spring, you can say just simply that there is no loss of kinetic energy. And so this is going to be our second equation, because watch this. So initial kinetic energy, I'll come back up here. This first one is moving. So I'll write it as 1/2 m1 v naught squared plus 0. And again, trying to show you that I'm accounting for the kinetic energy of both of them. And that's initial, before the collision.
Okay.
Now,
just to keep that as a whole placeholder.
Yeah. And now after the collision, it's 1/2 m1, and I'll write it in parentheses as we did back up here with the momentum. It would be a negative times the absolute value of number 1 squared. So there's the kinetic energy of number 1 after the collision. And number 2 would then look like this. And so maybe I'll put a little circle around it. And so what I'm trying to get at here is we have a problem of a system of equations. And that's why we can eliminate one of the variables. And if you look at number 6, they're saying, basically they're saying find V1 given V naught, but notice there's no V2 in there.
Mm-hmm.
And so what I'm going to do is then use these two equations and combine them and get rid of V2. And that's kind of my thinking here mathematically, okay? When I have two equations, I can combine them together, getting rid of a variable. And what would be the appropriate one? And for problem number 6, the appropriate one would be get rid of V2. But if you look ahead into number 7, the appropriate one would be to eliminate number 1 and then just be left with number 2.
Okay, yeah, that makes sense.
And so I would put 6 and 7. I'm going to write that down. Number 6 and number 7 as really kind of the same problem. It's just a matter of which one we're solving. So maybe I'm going to call this page 1 and continue on here.
So you would end up solving for that the top equation there for the variable that you're trying to get rid of.
Right. So let me solve maybe this top one for V2 and put it into here, see what happens.
Okay, and that would leave you with just your V1s in there and a V naught.
Yeah, so I've got M1 V naught from here. When I move this to the other side, this becomes plus M1 times the magnitude of V1 equals, and as long as I'm here, maybe I should put in what they told me earlier, M2. They told me M2 was twice M1. So I'm going to put 2 M1 V2. And of course, the reason I like that is because then there's an M1 in every term, and that can cancel out.
The 2, does the 2 cancel as well?
That doesn't look like the 2 cancels off.
Okay, I was thinking because you had 2 on the left, 1 on the right. I wasn't thinking about it like that.
So yeah, no, these aren't like terms, so I can't put them together.
Got it.
So this is V naught plus the magnitude of V1 equals 2 V2. Oh, and if you don't mind, I'll just divide by 2 and get what I said I was trying to get, which was to take that first equation and solve it for V2.
Looks good.
Okay, so now that I have a V2, let me pull out this second equation. Okay, and so the second equation, here's the 1/2, the M1, the V naught squared equals, and so this would be a 1/2 M1. And if it's okay with you, right here where it says negative squared, that just makes a positive. So that's V1 magnitude squared plus 1/2. And again, if you'll let me go ahead and just put here for M2, 2 M1. And then I can actually then put what we just solved for, which is right here. So I'll put that in a bracket and say, okay, that would be V naught plus the magnitude of V1 divided by 2, and that whole quantity. All right, well, let's see how this plays out. Maybe the first thing I would notice is that every term has a half in it. So I'm essentially going to either multiply by 2 or divide by 1/2, however you want to call it.
Was your you have the 2 M1 in parentheses there, right there, yeah. Was that supposed to be an M2 or an M1?
Okay, well, so that was supposed to be an M2, but remember, M2 is 2 M1.
Ah, I see. Okay. That makes sense.
Yeah. And in fact, that's the same little thing I did right back here. I just put in 2 M1 for M2. And the advantage was the M1s cancel off. And that's going to happen here too, is that then the M1s are in each term. They would cancel off.
Nice, a lot of canceling.
That's good. And so let's see what I have so far now. So now I have V naught squared equals, and I get this magnitude of V1 squared. Now let's take a look at this. It looks like this 2 downstairs when it's squared is a 4, and then it has that 2 in front of it. So I'm going to write those together as 1/2. And then I would have this quantity squared, which would be V naught squared plus 2 V naught times the absolute value of V1 plus the absolute value of V1 squared. So that's your A plus B squared. Um, okay. And it looks like now my best bet is to go ahead and solve for V1. And maybe since I have V1s and V naughts, but for number 6, we know what it is. They're telling us that V naught is 3.47. So I'll put 3.47 and square it. Looks like I'll have the magnitude of V1 squared here. This first term would then be 1/2 of 3.47 squared. I wonder if I should do some simplifying. Yeah, let's keep going. This right here, which 1/2 times this 2 would cancel off. So then I just have the 3.47 magnitude of V1 squared. And then I would have a 1/2 magnitude of V1 squared. So if I simplify this, it looks like this one here, this first term, and this one here are the same. So I've got 1 plus 1/2. So that's 3/2 V1 squared. Yeah, just looking, maybe I should have canceled things a little better, but I'll keep going here. Plus 3.47 V1. Oh, I think I messed up here. This was not supposed to be squared, was it? Because it was this term. Yeah, no square. Okay. And then these are just numbers. I'm going to have to grab my calculator here. This right here is 1/2 times 3.47 squared. And when I bring this over, it's going to be minus 3.47 squared. And so this is a minus 6.02. That would equal 0. All right. So
Where was that you got that one? Again, I'm sorry, the negative 6 points.
so I took this number here.
That
and
one,
then
okay.
this number here, moved it to the other side.
Okay. I see.
And of course, now I have a quadratic equation. And that's why I'm wondering if I shouldn't have put in my numbers. This probably factors. Probably could have made it a little easier. But I'll just go V1 then. And so V1 is the opposite of B, so minus 3.47, plus or minus the square root of B squared, 3.47 squared, minus 4 times A, which is 3/2, times a C, which is a negative 6.02. All over 2 times A. Now, again, probably would have been better if I factored this, but note that there's 2 answers. But notice the one with the negative sign. This first term's already negative, and if I use the one with the negative, it comes out to be negative. And that makes no sense since we're talking about the absolute value.
Okay.
So
I think that's how I ended up working this one out, I ended up using the quadratic formula as well. And that's how I was
Okay.
saying I was getting into some interesting stuff. So that's why I was asking about this question. So the absolute value would be take away that negative option.
Yeah,
Okay.
yeah. So taking away that negative option because of the absolute value, let me do the square root thing first. So 3.47 squared. And this minus make a plus. 4 times 3/2 times 6.02. And then I'll take the square root of all of that. So all of this is about a 6.9. And again, I'll take the positive one and I will subtract the 3.47. And then divide by 3. And I get 1.16. And I just looked up here and said, yeah, so that matches his answer. So good.
Okay, cool.
Yeah.
That makes sense. That's it's really nice seeing it written out like that.
Mm-hmm.
That's what I was trying to do. I was working with this solution because I was getting jammed up. And
Yeah. Now, right now, like the number's a little different, but watch the logic, if you will. Get my colored marker here. I'll do green first, or maybe I'll do red first. But then the reverse of this could work for number 7, because for number 7, actually, we got a couple of options. I was going to go all the way back, but now that I think about it, maybe I shouldn't. But if you go back to the very first 2 steps here, the first one here being conservation of momentum, and the second one being conservation of energy, you could just solve this one for V1 and put it into here. Another option, though, is kind of repeat what we just did, except your V naught would be different because that problem has a 4.22. And so you'd get a different V1. And then once you got a V1, you could put it into here and get the V2. I don't know which is better. Now, maybe I'll just go back to the beginning. So I'm going to come back here and then take this first equation and write it as M1 times V naught.
the one you're writing right now is the
Yeah. So
that
I'm
one
going to
there.
I'm going to write number 1 again. Whoops, I didn't mean to put equal. I'm going to actually let me do this. let me take this where it's a negative and move it over, so it becomes a plus M1 times the absolute value. So I've taken this negative one and moved it over. And then I'm going to bring this one to the other side, so it equals negative M1 V naught. And then right here is plus, and I'm going to do that same little trick again. Remember, M2 is 2M1, so I'll just put 2M1 for that M2, and then times V2. And again, like before, the nice thing about that is now the M1s cancel off, and I have an equation for the magnitude of number 1. And then I'm going to use that. So that's from, I'll call it equation 1. Maybe I should label it here, number 1. And then I'm going to put it into the energy equation, number 2. So here I go again. 1/2 m1 v naught squared equals 1/2, and then m1. And right here where it says magnitude squared, I got a negative, and so I'll just, first I'll just square that. So that becomes a positive. And so now it's got this quantity, negative v naught plus 2v2 quantity squared. So that's that term. Then plus 1/2. And I'm going to play that same little game there. Here's the M2. The M2 I'm going to write as 2m1. And then v2 squared. So again, like we had last time, each term has a 1/2, so we can cancel that off. Each term also has an m1 in it. We can cancel that off. And so we get v naught squared equals, and so if I square this becomes v naught squared minus, and when you multiply those two together, 2 times that, so that's 4 v naught v2. And then this one squared would be plus 4 v2 squared. And then this last term is just v2 squared. Oh, and actually, algebraically, this one looks a little easier because it looks like the v naughts are the same power or the same coefficient and on opposite sides. So they would actually cancel off also.
Okay.
And so if you move this to the other side, it now becomes plus 4 v naught v2. And then these two can be put together. You got 4 v2 squared and 1 v2 squared. So that makes a total of 5 v2 squared. And because those canceled, this is going to make the math a lot easier. We don't have to do a quadratic formula. We can just cancel off a v2. And we can even move the 5 to the other side. So we would have 4/5 of v naught is then equal to v2. So now grabbing our calculator, 4/5 of, let's see, number 7 gives us a speed of 4.22. And so, and I got a different number than the answer, which tells me, I think, I messed up some algebra somewhere. Let me double check. So let's try this first equation. I move this to the other side, so that would be a positive m1, v1 for magnitude, and then minus m1 v naught, and then 2m2 v2. M1s cancel off. Okay, that looks good. And then the other equation, 1/2 m1 v naught squared plus 1/2 m, and it'd be v naught plus 2v2 squared plus 1/2. Oh, there's my algebra. I got so excited. Right there. I canceled off that 1/2, but there still was that 2 hiding in there. I didn't catch that. Okay. So there's a 2 right there. So that would have made this 5a6, which then would make that a6, which of course reduces to 2/3 v naught. Okay, so let's try that, 2/3. So 2 divided by 3 times the 4.22, 2.81. Oh, good, and that matches. Okay, so yeah, a little careless mistake right there.
Okay.
Mhm. But hopefully the big picture you see with this is that for these collision ones, they usually are quite a bit of algebra because you've got 2 equations. You know, in a math class, you call that a system of equations. You got one equation you get for conservation of momentum, and you get another equation from conservation of energy. And they're usually pretty hard to solve because the energy one is a square. And so you've got to take a linear term and square it. And so you got to end up with a quadratic equation. I got kind of lucky on number 7, things canceled off, but in general, they won't. And so that's why number 6, we had to put it into the quadratic formula.
That was nice to see written out. Thank you.
Mm-hmm.
Yeah, it makes more sense how everything was derived.
Mm-hmm. Good. Good.
Oh, cool. Well, that was all my questions actually. So
All right. Well,
yeah, I'll probably go and keep working on this and
okay.
See what I can get done. Thank you very much for the help
You
and
bet.
for the advice on